Hello class, my name is Thomas, and for our final project I'm using the data collection and calculations I performed for our second lab about Torricelli's equations in the equational continuity. The lab's purpose was to find the relationship between the speed with which an incompressible fluid, water, flows from a small hole near the bottom of a container, and then relate this to the velocity of the surface as it falls. The procedure was, as all of you have done, mark the container, determine your R1 and R2 values, then find your A1 and A2 values. Also find your delta H value, which is the distance from the top of the container to the hole. This delta H is where it starts. As the water level reduces, your delta H reduces. We want to use the time it takes to get from one marking to the next to find our V1, the speed at which the water level decreases, and then use that in Bernoulli's to find your V2, the speed at which the water exits the small hole. So I used this video to time it as perfectly as I could to find the speed at which the water level decreased for each interval. But because the container is propped up on some items, we can also measure the distance it travels on the x-axis and the distance it falls on the z-axis. Using kinematics, we can find the travel time, and then plugging time into the distance traveled equation, but isolating v0. Now, using these two sets of data, I plug in all the known variables into both the kinematics equation and the Bernoulli's equation to find the velocity of the water exiting the hole at each water level, as it changes when the delta H changes. I also went ahead and calculated all of the uncertainties for every single step of the calculations. Then, I used the continuity equation to get a theoretical V2 to compare with. Using these theoretical V2s, I ran both the Bernoulli and kinematic V2 values into the percent error equation and percent difference equation to find the averages. Then, to test the continuity equation, I used the percent differences between the Bernoulli equations V2 and theoretical V2, as well as the kinematic equations V2 and theoretical V2. As you can see, 4 to 5 is an outlier, due to the fact that the velocity of the water exiting between Mark 4 and Mark 5 was so low that the water hugged the side of the container, so it was hard to take physical measurements. For Bernoulli's, there could have been some error due to the low velocity, causing the water to build up right outside of the hole and cause a bit of restriction. Finally, I took Q2, the experimental Q value for Bernoulli's, and plotted on a graph, axes being multiplied by 100 for scaling purposes. I then performed linear regression on it. For Bernoulli's, the V2 equation spit out 0.44 meters per second for all of them, rounded that is, and so it's the horizontal line with no R value. For the kinematic version, I did the same, actually getting a proper slope and a proper R value. This led me to believe that despite the imperfect percent differences, the continuity equation holds up nicely. Errors could have easily been introduced when it came to measuring distances due to messy turbulence and also just us messing up basic measuring. The initial velocity for Bernoulli's paired with the small delta H caused the change in V2 to be too small and thus the rounded output to be nearly identical. Thank you for watching.